Okay, good afternoon. So today it's a pleasure to have Professor Chang from NCKU to give us a talk. Let me briefly introduce Tay-Rong. So Tay-Rong obtained his PhD from National Tsinghua University in year 2013, and then he was a postdoc in Princeton before, and he also worked in the NCHU or Tsinghua University before that as a postdoc. He started his professorships in NCKU in 2017, and now he's a full professor in NCKU. So today, Tay-Rong is going to tell us about the electronic structure of topological materials. Let's welcome Tay-Rong.
Thank you. Good afternoon. I'm Tay-Rong from National Tsinghua University. First one, I thank Professor Zhang's invitation for giving me this opportunity to share my journey in topological materials over the past 10 years. Today, I'm going to deliver a 15 minutes overview talk focused on the electronic structure of topological materials, including insulators and semi-metals. I hope this talk can give you a preliminary understanding of topological materials. And I apologize if you are a super expert in this field. This talk may not bring you any new knowledge. Okay, before starting today's topic, if you are learning about this field for the first time, you are likely to ask this question: what is topological materials and what is topological physics? Why is it called topology, a fashion terminology that seems to have nothing to do with materials? To answer this question, my perspective is that we first need to understand how physics think about the phase transition. One famous approach is Landau theory. Landau theory is a powerful framework to formulate a general theory of a continuous phase transition. Roughly speaking, Landau theory describes that when a system undergoes a phase transition, the symmetry of the system is broken, which can be characterized by a measurable quantity called the order parameters. Okay, so here I show you a simple example. For a magnet at high temperature, it has rotational symmetry because it cannot attract anything in any direction. In contrast, at a low temperature, if you point a magnet in a certain direction, it will attract objects from different directions. So in this case, the rotational symmetry is broken. In addition, undergoes the phase transition, the spins in materials are ordered. So the order parameter in this case is the magnetization, which can be obtained from the hysteresis loop in experiments. And more precisely, we can write down the free energy in terms of the order parameter, and in this example is a magnetization. And after the simple derivation, we can get the relationship between the magnetization and the phase transition temperature Tc. Because the magnetization is a physical quantity, it must be a real number. So it only has a value. When T is smaller than Tc, because there is a minus sign in the square root. So this is the basic concept of the Landau theory. Okay, so based on the Landau theory, we can ask an obvious question. Can all the phase transition be described by the symmetry breaking and Landau theory? Before 1970, the answer was yes. For example, from the gas to a solid, it breaks the continuous translational symmetry. For a magnet, it breaks the rotational symmetry we have discussed earlier. Even the U1 gauge, such kind of unusual symmetry in superconductor, Landau theory can also catch it. So you can see that Landau theory is super powerful in the phase transition. However, as powerful as Landau theory is, there are still indescribable phase transition. So the famous exception is the quantum Hall effect. Before I introduce the quantum Hall, let me introduce the ordinary Hall effect first. For a conductor, if we apply an external electric field along the x direction and apply an external magnetic field along the z direction, then we will get a transverse current along the y direction. And in this panel, we see a longitudinal resistivity is a constant because it only depends on the detail of material properties, while the transverse resistivity increases when the magnetic field increases. So this is the ordinary Hall effect. Now, if we increase the value of the magnetic field larger and larger, and when the field larger than a specific value, we find the longitudinal resistivity separates into several discrete peaks. And the transverse resistivity shows an interesting quantized value. This phenomenon is called a quantum Hall effect because the transverse resistivity is quantized. And we can see that in this case, from the ordinary Hall effect to the quantum Hall effect, the symmetry of the system does not change because the magnetic field is always there. We just increase the value of the magnetic field. So this type of phase transition cannot be described by the Landau theory because the symmetry does not change. In addition, if we replace the external magnetic field with an internal magnetization, we'll get a phase similar to the quantum Hall, but without the external magnetic field, that is a quantum anomalous Hall effect. Quantum anomalous Hall effect is an important phase in condensed matter physics, and this important phase has been proposed by theory, but has not been confirmed in experience. So, how to realize the quantum anomalous Hall effect in a real material and understand the mechanism of its phase transition is an important issue in condensed matter physics. A theoretical work proposed, about 15 years ago, a theoretical work proposed that if there is a linear Dirac-like band dispersion in the bulk gap, and if we apply an external magnetic field or internal magnetization to open a gap at this Dirac point, in this situation, quantum anomalous Hall effect will be realized. But what material has this kind of band structure? Today, we know the answer is topological materials. So this is the outline of today's talk. In the first part, I will very briefly introduce the basic concept and the key properties of band topology in condensed matter physics. Then I will take you to tour a topological zoo, introduce various topological phases and their corresponding real materials. And in the end, I will share our recent new understanding in topological band theory to ask a question from Professor Wei Jimin Lao Shi, even he's not here. He asked me about 10 years ago. Now I know the answer. Because this is a colloquium, so I assume maybe some audience are not familiar with the band structure, band theory in condensed matter. So let me give a very brief introduction. In quantum mechanics, if we solve a quantum state of a single atom, we'll get several discrete energy states. Now, if we put many atoms together and separate by a lattice constant A, and the interaction between them cannot be ignored, in this case, the discrete energy states will connect with each other to form a continuous energy bands. We call them band structures. And the wave function of the band structure is a Bloch wave function, which is the plane wave times the periodic wave amplitude. So the horizontal axis of the band structure is the momentum wave vector k, and the vertical axis is the energy eigenvalues. Because the crystal lattice in real space is periodic, so energy bands in the momentum space is also periodic. And the period is from minus pi over a to plus pi over a, and we call this period Brillouin zone. Electron can occupy and move on the energy bands. So electron occupied state is the valence band, and the electron empty state is the conduction band. Band theory, band structure is very powerful and very important in condensed matter physics, because we can use this simple picture to identify the phase of matter. For example, if the valence band is fully occupied by the electron, and the valence band and the conduction band is separated by an energy gap, in this case, electron cannot move freely if we apply an external electric field. Because electron cannot move, there's no net current flow, so this is an insulator. In contrast, if the Fermi energy passes through the conduction band, electron can easily move on the conduction bands, so it is a metal. So you can see that even the band theory, band structure is quite simple, we still have enough power to identify the phase of materials. Black wave function propagate periodically in the materials, and the corresponding band structure we call the box state. In contrast to the box state, if the electron near the boundary of the system, this wave function will decay, and this type of wave function will create additional energy bands in the Bok gap region. We call this type of energy bands is surface states, and this concept this concept is the band theory we'll use in this talk. So next we'll discuss topology. In math, we are used to discussing the topology in real space, and we can identify the system topology by using the Gauss-Bonnet theorem. We don't need to go to the detail. The most important thing is that Gauss-Bonnet theorem gives us a G number. So G number equals 1 means there's a hole on the object, and G number equals 0 means there's no hole on the object. So the same G number represents the same topology, although their geometry are entirely different. So in this super famous example, a topology of a coffee cup is the same as a donut, but different from the Piola bomb. In physics, we are familiar with the band structure. So the topology is in the momentum space. In this example, we can see that the band shape or the band gap size of band structure 1 is quite similar to the band structure 2. However, their topology is different. For band structure 2 and band structure 3, they look completely different. However, their topology is identical. This result seems counterintuitive of a typical band theory, so let's discuss why this is so. Let's focus on the band structure 1 first, and here we project the orbital wave function onto the total wave function and plot it on the band structure to identify the orbital contribution on the bands. And in this panel, we see that the conduction band is mainly contributed from the A orbital, and the valence band is mainly contributed from the B orbital. For example, A orbital is bismuth orbital, and the B orbital is selenium orbital. Because the conduction band and the valence band is contributed from one species of orbital, so the vector of wave function on this band is well defined everywhere in the Brane zone, smooth and continuous. For the band structure 2 is quite similar to the band structure 1. Most of conduction band is contributed from the A orbital. However, at this point, it shows B orbital character. Because A orbital and the B orbital are different elements, so it is impossible to do a continuous deformation that A orbital become a B orbital. So the vector of wave function is no longer well defined everywhere in the Brane zone. It seems that there's a hole on the band structure, there's a hole on the wave function. This is why the topology of band structure 2 is different from the band structure 1, because the hole number is different. In addition, if we compare the band structure 2 and the band structure 1, we notice that the conduction band and the valence band exchange their orbital character. For example, we see the conduction band, we see the A orbital move from the conduction band to the valence band, and the B orbital from the valence band to the conduction band. We call this a band inversion. Actually, in a single particle frame, if we ignore any many-body effect, the topological phase transition must accompany a Bain inversion process. So, if the symmetry of the system does not change before and after the phase transition, and if the phase transition is induced by the Bain inversion, this type of phase transition is called the topological phase transition. And similar to the Gauss-Bonnet theorem, more precisely, we can formulate a mathematical quantity to identify the topological phase of in condensed matter systems. The terminology is a topological invariant number. And we can see that it is the Brenzon integral of the Berry curvature. So the geometrical phase, so the key of the band topology is the geometrical phase of the electron wave functions. So if the vector of wave function is well defined everywhere, this integral must equal 0. If there's a hole on the wave function, which will provide non-trivial Berry curvature, and this integral shows an integer number. In condensed matter, n equals 0 is topologically trivial state, and non-zero n is topologically non-trivial state. Okay, so so far I have very briefly introduced the basic concept of the band topology, but it is math. So what is the measurable quantity in experience? The answer is on the boundary of the system. So in this example, we can imagine when an electron propagates from the topological insulator to an ordinary band insulator or to the vacuum, it must experience a band inversion process. And because the evolution of a band structure is a continuous deformation, not a sudden change, so the band gap size will become smaller first, close, and then reopen when electron propagate from the TI site to the ordinary insulator site. And the band inversion critical point will occur at the interface of two systems. This is why the gapless boundary state or the gapless surface state is the hallmark of topological systems. So here is an example, typical topological insulator, bismuth selenide. RS data was from Hassan Princeton group. Simply, RS is the experimental method that can direct obtain the band structure in experiments. And in Taiwan, there are many experts in this field, such as Zheng Tian from IIMS. Okay, let's back. In our case, we see there are two linear lines around the Fermi energy, this dashed line, and there is the electron pocket close to the Fermi energy. And if we compare with our theoretical simulation, we can easily identify this electron pocket is the bottom of both conduction band, and these two linear lines are topological surface states. Now, if we artificially, theoretically make the band inversion, induce the topological phase transition, we see that these two linear lines disappear. So this is the direct evidence demonstrate that these two linear lines are the topological surface states. So here I very quickly summarize the key properties of the band topology. The first one is the band inversion can induce the topological phase transition. Otherwise, the topology is identical. No matter how we change the band gap, band shape, or even in this complicated case, the topology is identical until the band inversion occurs. And second, we can formulate a topological invariant number to identify the topological phase transition in condensed matter systems. For example, we have a chain number, Z2 index, or mirror chain number, and so on. Different type of topological invariant number for different topological systems. And the final one is the topological phase has a gapless topological surface state. So for a normal insulator, the box state and the surface state shows a gap, and for the normal metal, it's a box state and the surface state presents a Fermi surface. The topological insulator seems to combine these two entirely different phases. Its box state has a gap, while its surface state, its boundary state is gapless. So this is topological systems. Okay, so I have introduced the basic concept of the band topology in the first part. So in the next section, I will show you a few examples about topological insulating phase, including the strong topological insulator, weak topological insulator, and topological crystalline insulator. Okay, let's start with the strong topological insulator. The topological invariant number of a strong topological insulator is the Z2 index. Z2 classification refers to binary in mass, which means that Z2 only has 0 and 1. So Z2 equals 2 is the same as Z2 equals 0. And in condensed matter, Z2 consists of 4 numbers. The first one is the strong index, and the next 3 are the weak indexes. If the strong index of Z2 equals 1, which means that this phase is a strong topological insulator. And for the simplify, we generally omit the weak index and only write the strong index like this. For a strong topological insulator, if we tune the strength of the spin of the coupling from small to large, we'll see the band gap close and then reopen. And the band inversion will occur at the gamma point in the Boolean zone. At the same time, the strong index of Z2 will changes from 0 to 1, from an ordinary band insulator to a strong topological insulator. So in a strong TI phase, if we cleave the sample surface perpendicular to the Z-axis, we'll see a gapless linear surface state in the 001 surface Boolean zone. For a strong TI phase, no matter which termination you cleave, for example, if we cleave a 001 top surface or 010, 100 side surface, we will always find the gapless topological surface states. In contrast, if the band inversion occurs even number of times, for example, band inversion occur at the gamma and the Z point, in this case, the strong index of Z2 will changes from 1 to 0, and the weak index will appear. In this situation, the side surface shows an even number of gapless topological surface state at the time reversal invariant point in the surface Boolean zone, while the surface state on 001 top surface open a gap. And this gap termination is called a dark surface. In this case, you can see not all the terminations shows a gapless topological surface states. So this type of topological phase is called a weak topological insulator. The concept of weak TI was proposed by Liang Fu from MIT in 2007, but was not confirmed experimentally until 2019. And the candidate material is the beta phase BI4, I4. BI4I4 is a quasi one-dimensional system, so it provides opportunity to cleave our measure on different terminations. So this panel is the RPS result of the 001 top surface, and this panel is the dark surface. So we can see that there is no any signal around the Fermi energy. It's a gap. In contrast, at the side surface 100, if we follow these two momentum cut, the red and this orange cut, both of them shows the gapless RPS signal around the Fermi energy. So this is the direct evidence demonstrate beta phase BI4I4 is a weak topological insulator for the first time. According to our previous introduction, if the strong index of Z2 and weak index of Z2 both equals 0, this system will be considered an ordinary band insulator. However, if additional crystal symmetry, for example, mirror symmetry or the rotational symmetry, are taken into account, we can still find the gapless topological surface state in the surface brane zone, even the Z2 index equals 0. Because in this kind of system, the topological phase is protected by the crystal symmetry. So this type of topological phase is called a topological crystalline insulator. In such system, we can define the topological invariant number related to the crystal symmetry. For example, we can define the mirror chain number on the mirror plane or the rotational chain number on the rotational axis. In 2019, we theoretically predict the alpha phase BR4, and bulk bismuth rotational symmetry protected PCI states, despite the previous study shows that these two materials are ordinary insulator. So our work find the hidden topological phase and extend the classification of the topological materials. Okay, Bay inversion is crucial to induce the topological phase transition in the band theory. Even number of times Bay inversion will lead a strong topological insulator phase. And this phase can also exist in the anti-ferromagnetic system, which is called the anti-ferromagnetic topological insulator. Even number of times Bay inversion is more complicated. Non-zero weak index of Z2 or the Z4 index will give us a weak topological insulator or the ferromagnetic axion insulator respectively. And I will briefly introduce the axion insulator later. If this index equals 0, the topological state will rely on the crystal symmetry. Additional crystal symmetry, additional mirror symmetry or the rotational symmetry can protect the topological crystalline insulating phase. I have mentioned in the beginning of this talk, theoretically, quantum anomalous effect can be realized in a topological insulator. This is why we study topological materials. A seminal work published in 2013, Professor Xue Qin's group realized the quantum anomalous effect for the first time by doping the magnetic element chromium into topological insulator. And this panel is their most important result. So in this panel, we see a longitudinal conductivity, this red line, almost equal 0 around the Fermi energy, while the transverse conductivity shows a quantized value. So this is the smoking gun of the observation of the quantum anomalous effect. This is a very, very classical work. However, the magnetic doping in experiments is very hard to control, and the interaction between the magnetic elements is very weak. So you can see that the working temperature of this system is very low, only about 30 millikelvin. So there's the obvious question. Is it possible to realize the quantum anomalous effect in an intrinsic topological material without doping? In the end of 2019, scientists synthesized the first intrinsic topological materials, MnBi2PE4. For simplify, I call this MBT124. And the crystal structure of MBT124 is similar to the strong topological insulator bismuth telluride, but integrate Mn quantum layer integrate Mn layer into the bismuth telluride quantum layer. Unfortunately, the magnetic ground state of this new system is anti-ferromagnetic, which means that the spin moments upside in different layers. So this spin configuration does not create the quantum anomalous effect. We still need to apply the external magnetic field to flip the spin from the AFN to the ferromagnetic FN state to induce the quantum anomalous effect. So we have not realized the quantum anomalous effect until we find the ferromagnetic topological insulator. In 2020, my collaborator, Professor Nini from UCLA, she found she can systematically reduce the spin flipping energy when integrate the bismuth telluride separator layer into the bismuth MBT124 separator layer. For example, for the MBT124, we need to apply about 8 Tesla external magnetic field to flip the spin from the AFM to FM. For the MBT147 and MBT1610, the spin flipping energy will reduce to about only 0.2 Tesla. And when she integrate 3 bismuth stereo quantum layer between the MBT124 separator layer, the magnetic ground state automatically changes from AFM to FM. So this new material, MBT1813, has high possibility of being a ferromagnetic topological insulator. Here are some of experimental results. This is TEN, clearly shows the 2 MBT124 separator layer, same with the bismuth telluride quantum layer. And the hysteresis loop demonstrates the ferromagnetic ground state, and the spin orientation is along the z direction. In addition, our theory predict that the topological invariant number of MBT1813 Z4 index equals 2, indicate MBT1813 is a ferromagnetic topological insulator, or a fancy name, axion insulator. I probably do not have enough time to explain why this is called axion. If you are interested, please ask this question and I can answer in the Q&A. Here I just provide 2 possible experimental observations of the axion insulator. The first one is a surface Dirac gap. Because the MN layer in MBT1813 will provide a Zeeman exchange field to break the time reversal symmetry. So this time reversal symmetry will open a gap on the original topological surface state of the bismuth telluride. This panel is the obvious result, and this one is our surface spectral wave simulation. You can see they consist quite well, and both of them shows a clear surface Dirac gap. The second one is a half integer surface anomalous conductivity. The anomalous conductivity in axion insulator will achieve 0.5 on the surface. And to review these unusual properties, we construct this slave model and calculate the layer result anomalous conductivity. And this is our result correspond to this slave model. And our calculation shows that the anomalous conductivity is mainly contributed from the top and the bottom surface, and the conductivity decay very quickly in the bulk gap, in the bulk region. And this panel is the integral of the conductivity from the top surface to the bottom surface. And this shows the conductivity achieve 0.5 when we consider the top 10 layers from the surface, and the top surface and the bottom surface contributed from 1/2 of anomalous conductivity. So surface Dirac gap and half integer anomalous conductivity, these 2 evidence demonstrate that MBT1813 is indeed an axion insulator. Okay, topological material is a very huge research field, and I have introduced the topological insulating states. In 2015, part of research had been moved from the insulator to the semi-metal. So in the next section, we'll discuss the topological semi-metal. Generally, to realize the semi-metallic state in topological system is not easy, because generally the electron mass turn, this delta here, is not 0. Therefore, the band structure prefers open a gap when 2 bands approaching. In principle, you can fine-tune the chemical composition that valence band and conduction band touching and forming the gapless point. For example, we can dope the heavy element in an ordinary band insulator to induce the band inversion, and the band inversion critical point is the Dirac semi-metal. However, this approach is too fragile and very hard to control. Another approach is more reliable. Suitable crystal symmetry can eliminate the electron mass turn delta in the Hamiltonian and protect the gapless crossing point and stabilize the Dirac states. So the first Dirac set metal is Na3Bi, and this is the bulk band structure. We see it shows a clear band crossing point that is protected by the C3 rotational symmetry along the KZ axis. And after scan the whole bronzo, we find totally two gapless point. I label the cross mark in this panel. And this one is the 3D plot of the band structure vicinity, the bulk Dirac point. So this is Dirac set metal. And I have introduced the topological phase guarantee has a gapless topological service state. Dirac set metal is no exception. The difference is that in a surface bronzo, electron transport in topological insulator relies entirely on the gapless topological service state, while the Dirac set metal coexists with the bulk gapless Dirac point and gapless topological service state. And this prediction has been confirmed in RPAS. So this panel is the RPAS result of the Fermi surface of Na3Bi. Maybe not very clear, but these two spot points are the bulk Dirac point, and these two arcs are the topological service states. Next, I will show you a most famous topological semi-metal, wire semi-metal. The concept of the wire semi-metal comes from the wire fermion in NTU physics. So the wire fermion can be regarded as half of Dirac fermion with zero mass, carry upside chirality, and must come in pair. And sometimes high-energy physics and condensed matter physics has one-to-one correspondence. For example, we can find the Dirac fermion in graphene or in Dirac set metal. And in 2015, we found the first wire set metal, TAAS. So this finding gives us an opportunity to study the quasi-particle of the wire fermion in condensed matter systems. And wire set metal has the following three most important properties. I will introduce them one by one later. The first one is band structure. The band dispersion in the band dispersion of the wire set metal is graphene's three-dimensional analog. So you can see the linear band dispersion from the wire point in all momentum directions. So the low energy excitation state of the wire set metal will provide the quasi-particle of the wire fermion. In addition, different from the Dirac set metal, the Dirac point needs protected by the crystal symmetry. The wire point in wire set metal is very robust. It does not any symmetry to protect the wire point. And second is the topological invariant number. Wire point in wire set metal provide a non-zero Berry curvature, and the Berry curvature flows out from one wire point and into the other wire point. And if we compare the mathematical form of the Berry curvature and the classical electromagnetic, we can easily identify that the Berry connection corresponds to the vector potential, and the Berry curvature corresponds to the magnetic field. So because the Gauss integral around the one wire point shows an integer, not zero, so the wire point can be regarded as a magnetic monopole in the momentum space in the bronzo. And most importantly, this non-zero Gauss integral is the topological invariant number of the wire set metal. Because the chirality is conserved in the whole bronzo, the wire point must come in pair, and carry upside current. And the final one is a topological service state. Because there is a net very curvature flux between the two wire points, it has a gapless topological service state. And this exotic topological service state shows a arc feature, so we call this a Fermi arc. And this panel is a Fermi surface of the wire segmental TAAS. This one is a ring-in about the wire point, and we can see there's a Fermi arc connect to wire point. Beside the first wire segmental TAAS, we predict the wire state in a layered system WT2. And our results demonstrate that WT2 is a tunable wire segmental, which means that the separation, the distance of the wire point can be tuned. So in this panel, the horizontal axis is the MO doping concentration, and the vertical axis is the distance of the wire point. And we find the separation of the wire point increase as increasing MO doping concentration. And this one is a surface phase wave simulation, and this bright line is a Fermi arc. So this result demonstrates that WT2 is a tunable wire system. And our prediction has been confirmed in experience, not only for the RS, but also STM and the quasi-particle interference pattern. And I think because of time, let me skip this part. Okay, let me show you this new result. The wire state is not only exist in a three-dimensional system. This year, we predict the first 2D wire state in a 2D bismuth zinc covered on the substrate bilayer SNSE. And our theory shows that there are two linear wire-like band dispersion in the 2D bismuth zinc, which is similar to the graphene. And our prediction has been confirmed by the RTES. Beyond the graphene, we find that this linear wire state carry spin polarization. So this 2D wire state can be roughly regarded as a spin polarized version of graphene. And we expect that this new system may bring new electron transport or optical properties that is different from graphene, such as periodic anomaly, spin valley Hall effect, or nonlinear Hall effect we have predicted in our theory. So this is the next type of topological segmental I will introduce today. It's a nodal line segmental. Different from the Fermi surface of a normal metal shows a 2D Fermi surface. The bulk Fermi surface in a nodal line is a one-dimensional closed loop in a three-dimensional Boolean zone, this pink circle. And if we pass through this momentum cut, we find the band dispersion of the nodal line segmental is the same as graphene. So nodal line is likely stringing countless of graphene band in a closed one-dimensional chain. It is a red line in this panel. And at the surface, the H state of the ideal graphene is the perfectly flat band. And this flat band forms a disc-shaped surface state. So the topological surface state of the nodal line segmental like a drum head. So we call this a drum head surface state. And you can see the green area in this panel. And to formulate a nodal line, we only need two Pauli matrix. However, in three-dimensional system, the Hamiltonian consists of three Pauli matrix. So we need additional crystal symmetry to eliminate one of Pauli matrix and to stabilize the nodal line states. So in a real system, like tensor selenide, this system lacks the inversion symmetry but has the mirror symmetry perpendicular to the z-axis. And we can use this mirror symmetry to eliminate the Pauli matrix in the Hamiltonian and just stabilize the nodal line states. So you can see that in the constant energy contour, it shows a clear nodal line feature, this blue circle at the corner of the brain zone. And this prediction has been confirmed by the R-test. And the nodal line state can also exist in the anti-ferromagnetic system. So this year, we predict the anti-ferromagnetic Dirac nodal line state in YMN2, GE2. And in this system, the nodal line is located at the boundary, at the edge, at the boundary of the brain zone. So it is the largest nodal line in the real systems. Okay, so this is the last part. Originally, I would like to answer the question answered by the Professor Wei Laoshi, even he's not here. Okay, if we consider a two-dimensional topological system, we have a bulk gap and a gapless topological surface state. And this crossing point is protected by the time reversal symmetry. So if we apply a tiny Zeeman exchange field in the Hamiltonian to break the time reversal symmetry, this boundary state will open a gap. Because the boundary state is no longer connected valence band and the conduction band, in the band theory point of view, it is a trivial insulator. So Professor Wei Laoshi asked me, it seems that this system is quite fragile. However, we expect that the band topology to be very robust. So it's quite strange. So now my answer is that we need adopt another point of view. We need to include a new concept we call the feature spectrum topology. And because of the time, let me skip all the detail. And the conclusion is we can still find a gapless topological edge state. But this edge state is in the feature spectrum in another space, not in the band structures. So this system is still a topology. So a conclusion of today's talk, I have very briefly introduced various topological phases and their corresponding real materials. And here I collect the Fermi surface of the box state and the surface state in this table. Because there are many topological phases has been proposed. I hope this conclusion does not cause too much confusion. Another interesting thing is that Professor Castroneto from Graphene Center in Singapore once said that the children's favorite animal in a zoo is a tiger. Today I introduced to you a topological zoo. So where is tiger? I think the tiger is not any above materials, but a concept. It is a geometrical structure of the electron wave function that is induced by the band inversion. This concept is not only fundamental to the topological band theory, but also can be used to understand the exotic electron transport properties, such as nonlinear Hall effect in type 2 YSM metal or in the anti-ferromagnetic topological insulators. So quantum geometry engineering, how to manipulate the geometrical properties of electron wave function, I think may be a next direction of the topological materials. I thank all the collaborators. Thanks for the collaboration over the past 10 years, including the experimental group and the theoretical groups. And I also thank my group members. Thanks for their very hard effort. Without them, it is impossible to complete these nice works. And Xiaoting and Sogata, Shiboxin are a postdoc in US, and Moha now in Singapore as a postdoc. And Sophia, she just obtained the faculty position at the University of Tampa, Florida. And my current postdoc, Zhe Ming, he will join the Stanford University as a postdoc at the end of the year. Okay, thank you very much.
Right, let's take Tay-Rong. So, any questions from the audience, please? Okay.
Hello. Thank you for your very clear talk. So I want to ask that, as you show that sometimes theories may predict some spatial band structure or like topological insulator or semi-metal. So I want to ask that, is there any guide principle for experiments that which material should we synthesize or should we make to reproduce some kind of band structures?
Okay, so you are asking how we predict this system is a topological system or not? Or how we realize it
how we realize it?
Okay. First one is we are not a god, so it is very difficult to predict whether this system is a topological system before we do the theoretical simulation. But the direction is that the key I have mentioned in this talk is a band inversion. So even for the topological insulator, topological semi-metal, or even I introduced the feature spectrum topology, this new concept, the background, the key is the band inversion. So how to induce the band inversion is the direction how to induce the topological phase in the system. So one method is we can find a heavy element, because a heavy element has a strong spin of the coupling. So it provides an opportunity to push the band span up and conduction band down, and we may induce the band inversion. The other directions we can apply and we can change some parameters in experiment. For example, we can apply external field. For example, external electric field perpendicular to the sample, break the inversion symmetry and split the band and induce the topological phase transition, or apply the high correlation. This is the other method to induce the band inversion. The key is the band inversion.
Okay, thank you.
Right, anyone else?
Yeah. Would you please elaborate a little bit more about the 2D wire system you talk about?
Okay. So, okay, let me.
Please first.
Okay, so in this system, we put this is the black phosphorus structure, and we can put the bismuth with black phosphorus structure on this bilayer SNS subject, and we found okay, this is the band structure of black phosphorus. I call it alpha phase without spin of the coupling. So you can see this is band span, and this conduction band has a band inversion. And after we include the rush bus, after we include the spin coupling, it's open again. Now, if we put it on the subject, it has an internal electric field, so it breaks the inversion symmetry. It will induce the band splitting. And in this case, it just touch together. So this band is singly degenerate, and this point is doubly degenerate. So it is a wild state. And yes, and this is our topological invariant number calculation. Demonstrated that this Gabriel's point is carry non-zero
topological charge, the Winding number. And we predict the Japanese edge state at the boundary of the system. And this prediction has also confirmed by the STM. So we can change the BIOS of the STM, and here is the here's the BI, SBI, and here is the subject SNS. And at the very low energy, far away from the Fermi energy, you can see only BI as bright. However, if we tune the Fermi energy around the Fermi energy, here around the Fermi energy, these two, you can see the interface, the edge of this subject and the BI is bright, so it is a edge state. Now, if we increase the energy to a very high position, this bright light disappears. So this demonstrates that this material is indeed a topological state.
Tay-Rong, in the beginning of your talk, you very nicely introduced the connection to the solid state physics we usually learn in the undergraduate and graduate. And there, I think there's a place where you try to introduce the connection to the atomic orbital or the projection of the orbital, where you introduce the A and B orbital, and that's how the topology comes into play. I was wondering whether that is always the case you need it for the topological insulator, in the way that you say you have the bulk insulating part, and only on the surface of that insulator you have this conduction channel, right? And I think probably it's not a bad situation to ask you the question. So if I just take a usual boring insulator, but then I will just coat it with one atomic layer of any conducting metal like silver. So this means in this strange thing, inside is insulating. Outside, I just have the silver layer that is conducting channel, and that is only on the surface. Then in this case, we probably don't have your changing of the orbital between A and B, yes, but it looks like the property that you are looking for, right?
Okay. Yeah, very
so I probably don't fake your physics, but I mean, it seems to be strange, right?
Okay, it's a very interesting question. Okay, it's quite different because the topology is a bulk properties. So this is why the topological system has a surface state, because we have a bulk invariant number. Okay, and the most important thing is the I didn't show here very clearly, but this Japanese topological surface state is must connect the brainspan and conduction band. So, which means that if you apply any perturbation on the surface of your system, for example, you put something on the surface or apply an external field, this surface state will always there. It is impossible to open a gap or remove it of this surface state. But if you just put a thin metal on the insulator, in principle, I can find a way to move the conduction state of the your cover metal.
Okay,
so it means that I can find a gap in the metal, but here it is impossible to find a gap.
So this means in your case, the topology is protecting the surface state, because you can destroy the surface, but then those states should still somehow be there.
Yes. So I think a very interesting phenomenon is that if you put, for example, a topological insulator in the air, and the oxide will cover on the surface, and in principle, some kind of topological material in surface will be destroyed by the oxygen atoms. It seems that this system becomes trivial insulator, but when you clean the surface, the Japanese topological state will appear again.
And this protection property is related to the orbital, the A and B, that exactly. They are interchanging that direction.
Yes.
Okay, thank you.
To cure topological state, the only way is induce the bulk base version.
Okay, thank you.
All right. That reminds me something because we are doing laser spectroscopy, so the band inversions is something that we're interested in indeed. Something called flocate physics, where you basically just drive it strong enough with the laser pulse, you can bring the conduction of the valence band to the top of the conduction bands.
Yes.
Is there any possibility to see the topological insulating state?
Exactly.
Oh, really?
Yeah, it's a 4K induced topological
Right.
vision transition. Yeah, but it's a time dependent, right?
Of course, yes.
Yeah. So when you valence state transfer to the conduction state, it can induce the Bay inversion.
Right.
And in this time period, it's a topologically non-trivial state.
Right.
And when the system back to the ground state, it becomes a
of
trivial
course.
again.
Yes. Yeah.
Yes, and it's a
So
possible, but I have not seen it in real experiments. But I think the idea is possible.
well, in that sense, we can actually do any insulator, trivial insulator, drive them into the topological insulator.
Yeah, exactly. Yeah.
Okay.
Yeah.
Well, there's something new.
So actually, I think the topology is a very general phenomenon. It's not great.
Right.
Yeah. If we really understand this concept, it's very general.
But I think my question is that even we can drive this flocate physics out, but we are not sure we can prove the topological properties out. Like you know the unidirectional transport properties, for example.
Yeah.
Okay.
So in principle, theoretically, we can do this, but I have not seen any experiments to realize this.
Okay, got it. All right.
Just regarding your discussion, so one of the early smoking gun evidence for the topological phenomenon has been the spin momentum law property of this topological concept. So then in any case, just like what Zheng Tian has raised, we can of course put a piece of metal on top of an insulator and then find some surface insulating state. That would be corrective phenomenon, just like plasmon and then your corrective magnetic property. But it doesn't carry this kind of single particle spin momentum law character, which means that on one surface you have this spin up and the other is spin down. So if in one day you want to prove your flocate induce a topological property, one of the smoking gun evidence you will need to prove that can you put high magnetic field and then to see whether you can see some kind of spin momentum law property, and it will be definitely very exciting. So in my electron microscope, I naturally have a 2 Tesla field inside. So actually, I want to put a piece of wire semi-metal in because the magnetic field is always there. And according to the theory, you are going to have a Y orbital. And the Y orbital is going to have a certain frequency. And then whether this is true or not, actually recently, Li Weili in Zhongyuan Wuliso, he has proved that he sees the Y orbital, but in other experimental systems, interestingly, Y orbital has not been 100% proven yet in other material systems. So if you can do something new, definitely, I think Tay-Rong's work will be very, very inspiring to all of us. Yeah, thank you.
All right. Okay.
This might be a naive question. So I understand that Berry curvature is related to the momentum space, and you mentioned about quantum metric in your last slide. So I wonder what's the difference between quantum metric and Berry curvature?
Oh, okay, very, very good question. How I say? I think it's just a different point of view. It's very similar. It's just different point of view. My explanation is that it's related to the concept of the fiber bundle. Okay, so it's base is our two-dimensional Grand zone, and we can put a fiber. The fiber is a Hilbert space here, or perpendicular to the brain zone, and it's an additional dimension. And how evolution of the Hilbert space when we go through the brain zone, this is a very curvature. And because this Hilbert space is a stop Hilbert space, and if we consider full Hilbert space, this fiber stop Hilbert space just a point on this full Hilbert space. So when we go along this path, it's just like this path on the full Hilbert space, and this distance can be regarded as the distance of the block wave function, and this is the metric. So, for simply say is that the very curvature we consider is in the momentum space. Now the concept of the metric is in the Hilbert space, but they talk about very similar thing.
Okay, anyone else? Last questions, for example. Right, if not, let's thank the speaker again.